A code scanning alert points to a real weakness. The code is still present, but an external control, perhaps a network policy or an application firewall, reduces the practical risk. What should the team do? Ignore it? Mark it as won't fix? Or record the risk reduction without pretending the weakness disappeared? GitHub has added a new dismissal reason called mitigated for exactly that situation. It sounds small, but it can either improve engineering discipline or turn a security backlog into a comfort blanket. In this CipherVibe RFV1 briefing, we will make the difference visible. Fixed code, accepted risk, and genuinely mitigated risk are three different states. Then we will run a completely local, fictional policy simulation that shows the evidence a responsible mitigated decision needs. GitHub's August 20th update says teams can now dismiss a code scanning alert as mitigated when a vulnerability remains in the code, but external controls reduce its risk. GitHub gives a web application firewall and a network policy as examples. The goal is to distinguish the state from alerts marked won't fix, align dismissals with formal exception and risk acceptance processes, and reduce the need to track those decisions somewhere outside GitHub. That is useful because security work often happens at several layers. A developer may own the code, a platform team may enforce network reachability, and a security team may own the exception review. The new label can connect those facts, but it is only honest if the control is real, relevant, monitored, and temporary or reviewable where appropriate. Think in layers. Code scanning identifies a condition that may become a vulnerability. That finding matters, even before a public route is exposed. Next, ask whether untrusted traffic can reach the relevant behavior. Then ask whether an independent control blocks, narrows, or monitors the path. A restrictive network policy might make a service reachable only from a trusted internal workload. A carefully configured edge control might reject a harmful request pattern before it reaches an application. Those facts can reduce risk. They do not erase the condition from code. The remaining question is residual risk. What changes if a route is opened later, a policy drifts, an internal identity is compromised, or the control is bypassed? A mature mitigated decision says what is protected, what is not, and when the team will revisit the code-level fix. Pause and choose. The answer is C, but only with evidence. It is not fixed because the code finding remains. It is not automatically won't fix because internal services can still be reached through trusted identities, integrations, configuration changes, or future exposure. Mitigated is the precise label when the compensating control is documented and reviewed. The record should name the affected surface, the control, its owner, how its effectiveness was verified, the remaining risk, the date of review, and the trigger that reopens the decision. This is why labels matter. A good status tells the next engineer what they can rely on. A vague status makes them guess whether a closed alert was remediated, deferred, or simply forgotten. Here is our safe local lab. It contains a fictional service, a synthetic alert called CV-SYN-042, and an invented external edge policy. No repository is opened. No code scan is run. No account, token, query, browser action, payload, or network connection is used. The simulator evaluates two exception records. The first says an external control exists, but it has no named owner, no test evidence, and no review date. The local policy blocks that dismissal. The second record includes the control scope, proof of its behavior, an accountable owner, a residual risk note, an expiration date, and a planned code fix. The simulator permits a mitigated recommendation and writes a local evidence report. This is a training model, not a claim about any real GitHub configuration. Use 6 fields to make a mitigation reviewable. First, identify the exact alert and affected code path. Broad statements like covered by the platform are too vague. Second, describe the compensating control and its scope. Third, attach effectiveness evidence, a configuration review, an authorized test result, a policy assertion, or monitored telemetry. Fourth, name the owner and the signal that shows the control still works. Fifth, state the residual risk and assumptions. Sixth, record an expiry or review date and the plan for the code-level correction. The value is not bureaucracy for its own sake. These fields catch the common failure mode. A control that was once valid silently changes while the dismissed alert stays closed. Evidence gives a future reviewer a way to understand, challenge, or reopen the decision. The most dangerous shortcut is treating any perimeter control as a universal fix. A web application firewall may reduce a specific inbound request risk, but it may not cover an internal route, a different protocol, a background worker, a batch interface, or a future deployment. A network policy can reduce reachability, but it depends on the policy being correctly applied to every relevant workload and identity path. Mitigations fail when teams copy a control name into an exception ticket without connecting it to the alert's data flow. Ask the uncomfortable question: if this exact safeguard failed, changed, or was bypassed, what would happen? If the answer is serious, the code fix should stay visible in the engineering plan. Mitigated should make that plan clearer, not make it disappear. The answer is C. Reopen a mitigated alert when the service exposure changes, the compensating control changes, ownership changes, the planned review date arrives, monitoring stops, evidence becomes stale, or the code moves into a new environment. These are not signs that the original decision was bad. They're signs that risk is a living system. The alert should also reopen when a developer makes an adjacent code change that alters the findings context. This is where a native dismissal reason helps. The code scanning record can remain connected to the decision rather than being split across spreadsheets, tickets, and memory. But the process still needs a human owner. Tools can preserve context. Teams must decide whether the context remains true. A mitigation decision is rarely owned by only one person. Developers understand the code and the future fix. Platform engineers understand the gateway, policy, identity, or deployment guardrail. Security reviewers assess whether the remaining risk fits the organization's appetite and whether the evidence supports the claim. Give each group a visible responsibility. Developers should not have to guess whether a perimeter control still exists. Platform teams should not become permanent owners of a code weakness by accident. Security teams should not approve an exception with no expiry or technical proof. CipherVibe's practical rule is simple: separate the accountabilities, join the evidence, and make the next review obvious. That makes the change useful for audits and more useful for the engineers who inherit the system. GitHub's new mitigated reason gives teams a better language for a common reality. Sometimes risk is reduced outside the code before the code can be changed. Use that language precisely. Keep fixed, won't fix, accepted risk, and mitigated separate. Document the control, prove that it applies, name the owner, state the residual risk, set a review date, and keep the durable code fix visible. Then use reopen triggers whenever the system changes around the exception. That approach turns a dismissal into an engineering record rather than a disappearing alert. For more practical security explainers, safe simulations, and defensible workflows, visit CipherVibe.com and subscribe to CipherVibe. Build safer, ship smarter.